Hi, I'm Randall Heyman. I'm a university mathematics academic. Welcome to my Corona Help playlists, where I make quick turnaround videos to help students and educators during the virus outbreak. If you'd like me to make a video for you, then you can just email me or make a comment below any one of my videos. Okay, so today, I hope you're well. I'm going to do an overview video on ordinary differential equations, which are also called ODEs. And this is for Zach, who's also in Sydney like me. And what I just wanted to do in this video is just do an overview, because there's quite a number of, well, there's quite a variety of different ordinary differential equations. I'm only going to give you the ones that you'll typically see maybe in first year at university or college. I'll give you a little sort of one sentence idea on how to solve them, but the purpose is not to solve it. It's really just to give you an overview, and so that you can hopefully distinguish between the different ODEs, because you may get a question where they just give you an ODE and you have to work out the best way to solve it. So you have to know what you're up against. Okay, so let's start by talking about ODEs, ordinary differential equations. So what are they? Well, what we need, in fact, let's do it this way. I'll make that a heading. So the first thing that we need is an independent variable. And then here I'm just thinking of something like x. Well, let me write e.g. x. Example x. And then what we need is one or more derivatives of a function of the independent variable. So example, the function will be fx, say, fx, and that would lead to, for example, once again, just an example, something like df squared, dx squared. So the second derivative of f with respect to x. Okay, so pushing on, let's just give you now some examples. And there's a number of ways that you'll see differential equations in different forms. So I'll just use them interchangeably through this video. So one would be like dy dx plus x equals 2. That's a differential equation, an ordinary differential equation. You could also see it written like this, f dash x plus x equals 2. And you'll also sometimes see it y dash plus x equals 2. So you need to get used to seeing all of them like that. Let's put another example. This is now to do with the order of the differential equation, which we'll need in distinguishing between the differential equations. So we might have something like this, d to the fourth y, y dx to the fourth. So the fourth derivative of y with respect to x plus the second derivative of y with respect to x plus 10y equals sine x. So that conforms with everything I've said about ordinary differential equations. And in this case, because of this 4 here, that's the highest derivative. So the order of this particular differential equation is equal to 4. Okay, so now let's start looking at some of the different differential equations that you might see. Sorry about this. This is a hangover, a leftover from the Chinese remainder theorem. I thought I'd actually got rid of them all before I started. There's tons of it. Okay, let's go back up here. And we'll talk about separable ODEs. That's the first thing I want to talk about. So let's actually number it just so that we now one separable. Let me just make sure I spell separable correctly. I think that's right. Separable. Separable ODE. Okay, so the key idea here is that you can put all. I'll generally now be using y and x. X will be the independent variable. Y will be the function that depends on the independent variable. So you can put all the y's to one side and all the x's to the other. And I mean, it's implicit here, well, it's implied ordinary differential equation. Key word here in this, for what I want to say, is equation. So, and all the way to the other side. So let's look at an example. Dy dx. This is a really simple one. Equals xy. So what we would do is we could sort of write this sort of thing. 1 on y dy equals x dx. So this is saying 1 on y times some infinitely small change in y gives you the same as the change in x times a very, very, very small change in x. Okay, and solution. Remember, I'm not showing you how to solve these. If you've got questions on how to solve, you're going to comment or email me if you want, and I'll do another video. Solution. Yeah, you integrate both sides. So you literally just put an integral sign there, an integral sign there, and go from there. Okay, so that's that one. Let's go on, because I don't want to make this a half an hour video. So we've done separable. Now let's talk about first order linear ODEs. Okay, so that first order, of course, tells us that we can't have higher derivatives. The highest derivative is going to be, well, sorry, the only derivative we're going to have is dy dx. We can't have the second or third derivative because it's a first order linear differential equation. And then we're going to just have some function of x times y. Maybe I shouldn't use f here because it'll confuse you with what I've written before. So let's make this gx equals h of x. So example, dy dx. Actually, very important little tip for you if you start doing these, you must make sure that there's nothing in front of the dy dx, not even a 2 or a 5 or a -6 or anything like that. If necessary, you're just going to divide both sides to get just the dy dx. Here's one. So that's a first order linear differential equation. Now, let's talk a little bit about, well, as I said, one little line on how to solve. Solution. You're going to multiply both sides by an integrating factor. And essentially, that integrating factor is you're going to integrate. Look, I won't go into the details. I don't really want to get too involved in it all. Let's just leave that at that. Okay, now the next one that we've got is an exact ordinary differential equation. And this is of the form fx fxy. So it's a function that's dependent on both x and y. So here now I've got two independent variables. Well, sorry, no, I've got x and y. That's right. It's got x and y as we had before. Anyway, look, I'll do an example. You'll see how it works. Times dy dx equals 0. So it has to be in that form, and also with, so the partial derivative of df with respect to y must equal the partial derivative of g with respect to x. So often you'll get a question saying to see whether an ODE is exact, and to see that you'll check that it's in this form that we had up here, and then you'll also check to see the partial derivatives. Let me give you an example, and this one comes actually from, I've taken this from the UNSW, one of the UNSW courses, where I tutor from time to time. 2xy plus x squared plus y squared times dy dx equals 0. So first thing is that we can look up here and see that it's basically of that form. Why is that? Well, fxy is equal to 2xy, and gxy, so this is a function g that depends on x and y, and it's x squared plus y squared. And so that satisfies the first thing. And then the second thing, which if you just look up here, we need to ensure that that's correct. So the partial derivative of f with respect to y, remember the partial derivative just means that we take the derivative where we just take that x as, treat it like being a constant. So if we take the partial derivative of this with respect to y, well, that's just 2x. And if we take the partial derivative of g with respect to x, which is this one here, well, we just get 2x. The y squared, treat it like a constant. If you took the derivative of a constant, you just have 0. So you can see that the two partial derivatives are the same, and so this is an exact, an exact ODE. Solution, it's complicated. We basically assume a solution h of xy equals c, and then we need to play around with a whole lot of partial derivatives. There's different ways to do it, but broadly speaking, we're going to be, this sort of stuff's going to be part of what we play around with to solve it. Okay, one more left. So what number was that one actually? 3. Okay, so let's do now finally number 4. And this is where we get to second order. So, whoops. All of these different forms directly transfer to really practical everyday applications. Second order linear ODEs with constant coefficients. And this will be of the form like this: d squared y dx squared plus c dy dx. Oops, a partial. It's not a partial. Actually, it's, yeah, sorry, that's confusing. Well, it's not only confusing, it's wrong. dy dx squared plus c times dy dx plus d times y equals, let's call it g of x, just any function of x. And here c, d are constants. So let's do an example. And here I'm just going to change to that other, one of those other forms. Rather than write d squared y dx squared, I'll just write y double dash plus 4y plus 10 equals e to the x plus sine x. So that would be fine. That is a second order linear ODE with constant coefficients. And solution, well, the first thing is that we have to create or use, so I'll say use the characteristic equation. In fact, we have to solve the characteristic equation. And the characteristic equation just comes directly from here. We replace the y double dash with lambda squared. We replace the 4y with 4 lambda, and we replace the 10 with just 10 equals 0. And when you solve this, which may give you complex solutions, that's fine. Then that will give you, that then gives you the start to solving the problem. Once again, I'm not going to go into details. If you've got specific questions, then you can ask, and I can do a real example. Okay, so if you've got any questions on any of these differential equations, then comment me or email me. I do have a video I made about 4 or 5 years ago on one of these, and I can't remember which one it is. But if you ask me about that one, then I'll check and I'll refer you to one of my videos of some time ago. Otherwise, I'm happy to do the others for you. So I hope that's been useful to Zach and anyone else that's watching. And if you've got any questions, let me know.